Your calculator's not going to show you this. There's actually a hole at 0. So if you were to go and say, hey, look, but x over x is 1, this is incorrect. No, look, I'm not trying to rock the world of your logic here. X over x is 1, so long as x isn't 0. If x is 0, then it's not 1. So the rule of thumb is this. If you ever simplify something algebraically, you have to keep track of what it is that you cancel out and make sure that it's never 0. It's exactly what we did here. We canceled x plus 2's. That's OK to do, as long as you promise me x is never going to be negative 2. Because if you try and plug negative 2 in here, go back here and try and plug in negative 2, you're going to get 0 over 0. So that means we have to remove negative 2 from the picture, take it out, and that's going to give us a hole. Understand? Now, what's the difference between a hole and a vertical asymptote? Well, negative 2 should make the bottom 0, right? But it makes the top 0 at the same time, and that's why it's a hole and not a vertical. Verticals happen when the bottom is 0 but the top's not. That's when you have that whoosh, taken off like this. So what we do when we graph rational functions is we take the holes out first, get all those out, and then we proceed. Understand? Yeah, you'll see when we do this one, when we finish up the picture, you'll see at the very end. Just don't let me forget that we had a hole, okay? All right, so now we move on to the next step. Find the x-intercepts. So how do we do that? We set the numerator equal to 0. So now I'm ready to get down to business. X-intercepts, set the numerator to 0. And by the way, when I say numerator, we are going to work with this stuff canceled out. It's gone, all right? So what's the numerator I'm working with? X minus 3. Where is that 0? X is 3. That wasn't so bad, right? That's for what? When do we set the denominator equal 0? To find what? The vertical asymptotes. Okay, so that's our next step, vertical asymptotes. We set the denominator equal 0, which is what's left here? X minus 2 is 0, so x is 2. Okay, yep. And what's next? The horizontal. Now this is tricky. This is tricky. We have, again, the way we did it last time is we looked at the behavior, didn't we? We looked at this behavior. We said, all right, take what's left, x minus 3 over x minus 2. And let's look at what's the dominating factor, or the dominating term. The dominating term here is x, right? And we can even say 1x, right? The dominating term here is what? 1x again, right? The minus 3 and the minus 2 don't make much of a difference. Now, simplify that, and what does that get closer to? 1. So your vertical asymptote is y is 1. Horizontal, thank you for correcting me. Yeah, I just threw a wrench into it all there. Horizontal right here. All right. Now what we do, so let's see. The way that I did it in my notes, you can ignore that. For horizontal, there's a less intuitive way of doing it where you just like have 3 different cases, and I don't want you to do it that way. You're going to calculus. You need to understand it more like this than just following some like, okay, if this, I'm going to do this, and this requires a little more thought, right? Just a little bit? Okay. So after you've got everything together, plot all the information you have so far. Then we're going to get our test points. How many test points am I going to have, by the way? 3. Because I have 1 x-intercept, 1 vertical asymptote. So I have 1 of these and 1 of these. So that's a total of 2. So I need 1 more. We don't look at the horizontal at all for test points. It's just these 2. Okay?
So if you have 3, you need 1 more.
You need 1 more than what the total number that you have. Okay. Here we go. I don't need that. Picture time. This one's going a little faster than the other one, huh? Yeah. Okay. Maybe. So what do I start with? X-intercepts, where were they? I only had one. It was at 3? That's a dot, right? Remember what you're drawing. An x-intercept is a dot on the x-axis. What's the next thing I had? Vertical. One of my colleagues thought that this was hilarious. I'll get this on camera too. I think it's pretty funny. Paper only. These plastic bottles fall out everywhere. To me, it's like, my wife gets mad at me because I'm not big on recycling. I'm one of those people who will just be like, you know, just throw it all in the garbage.
You say this is math class, we don't read. We don't read stuff.
Yeah.
We all about the numbers.
See, I believe in the ultimate recycler. The ultimate recycler is the sun. At some point, the sun, as it begins its journey into its own death, will expand first. And as it expands, it'll pretty much recycle everything here. And then, so it's all going to get recycled at some point in time. Okay? I know that that's not a good, that doesn't help future generations, but I don't think much is going to help future generations.
Well, I hope that doesn't pass along to anyone else.
That what doesn't?
That your idea, like, people are just gonna be like, oh, it's okay, like, over-recycle.
You mean to tell me that people actually care?
Yes, some
Really?
people care.
You mean to tell me that we value sports and all these other things over education, paying teachers, paying scientists, that we have a dead-end physics program because there's no money in physics. No one wants to put in the money to get us to actually do something good. You know what I'm saying? You get a bunch of people who are very excited. They want to make change, but you got to get people to believe that you got to put money into the right places for that to happen. So we can sit here and like lie to ourselves and be like, yeah, let's recycle, let's do it. If you don't do it right, you're wasting your time. So I believe you and I agree. Let's recycle if we're going to do it right. If we're going to do it right, let's do it. But if it's going to cost, if the energy spent to actually recycle creates more pollution than what you're saving, then what? I mean, it's like taking crap out of this pocket and putting it in that pocket.
Which is like that, the corn ethanol stuff.
Yeah.
Actually costs $1.25 worth of diesel to get $1 worth of gasoline out of it.
You know.
I mean, that makes sense when it comes to fracking. So.
Okay, I'm sorry. I think we just turned this into like some sociology course. Whew, let's get back. I'm just saying, like those. We can argue and we can save the planet right now, but eventually, we've got to get off the planet, right? You've got to get off the planet eventually, unless you got plans to move it. Okay. See, I have to believe in this younger generation. You all have to believe that there's still that possibility, you know, that we can still do something like that. Get off the planet, right? You agree? You got to get off the planet? Do we agree? Or we don't care now? They'll deal with it later? They'll deal with shit. They'll deal with it later. They'll figure out a way. Who cares? Just wait for the next Super Bowl so we can all have reason to have fun. All right. Where are we? Whew, that happened fast, huh? What's next? X-intercept. Vertical. Where was it? 2. Okay, what do I draw here?
Just like kind of a dotted line.
Dotted. Okay, so just don't forget this. I see students that'll do this. They'll put a dot here and then they'll draw a dotted line. And then later on when they're trying to draw their picture, because they're not drawing in color like I am, they get confused. Like that dot, they think it's part of their graph. Okay, so I don't want a dot there. I want a dotted line. Too bad this isn't a sociology class. We could actually talk about things that are open for, you know, subjective debate as opposed to math. No one's going to argue with me about what the vertical asymptote is here. Huh? All right. What's next? Horizontal. Let's take care of horizontal next. No, I'm just going in the order. The whole is going to come in at the very end. Okay, we'll put the whole back. So horizontal, where was it?
1.
Y is 1, right? So I need to go up on the y-axis 1. Remember, it's a horizontal line, and then I'm going to draw a dotted line, Which way? All the way? What did I tell you?
Yes.
Ends only. Ends only. So I've got some information here about my graph. I've got some information here. So I would say an end is going to be over here somewhere. I'm going to have an end somewhere over here. Safe? That's safe for you?
Sure, why not?
All right. Okay. Here's the reason why I've avoided the hole. Where was the hole? -2. The reason why is because I don't really know where my graph is yet. Once I have my graph, all I'm going to do is draw, and then I'm going to go in there and erase it and put a little hole. You see? That's all I'm going to do. Okay, so what's next? What's next? Test points. And we have to have, how many test points did we say?
3.
3. And now I didn't say this earlier, but I'll try and say it's weird wording. You need to pick a test point between each x-intercept, or between each vertical, or between each x and vertical, and you have to pick test points on the end. So, okay, what do I mean? You've got to have test points at the ends. Let's take care of that first. So here I've got an x-intercept. I've got to have at least one test point over here. 4? Okay, I'm drawing it, little x, not a dot. And I got to have something over here. -2. Oh, wait, hold on, -2. Can't use -2.
How about a -1?
-1? And I have to have one between the vertical and x-intercept. See, I've got to know what's happening right in here, right? Got to pick something right in here. What did you say? 2.99. You could do 2.5 though also, right? This was 2? That's 3. That's all you should need. And we're going to plug those in where? To the original function. And we should be able to plug it into its factored canceled one.
I was going to ask you. So it's just the factored one?
Yeah, which I forgot what it was.
-3.
I should know that. I should be able to look at this graph and know that. But x minus 2, yes. Okay, let's plug in -1 first. This should be pretty clean and easy, right? -1 minus 3, -4. -3, negative over negative, positive. So I know over here I'm a positive. How far up do I go? Doesn't matter. Okay? Doesn't matter. I don't care. You don't have to put it above this dotted line or anywhere. So where do you want it? Above or below?
There.
Right here? Okay, there you go. That's it. There it is. Okay? Now, how about 2.5? Plug 2.5 into this. Negative on top? Positive on the bottom, so negative over positive is negative. So over here, I'm going to erase this thing. I have a dot below. And then at 4, plug in, and you get positive. So I'm going to put this one up here, just for fun. And that's it. That's all you need. I should be able to draw this now. I'm going to start at the point furthest to the left that I have for sure on my graph, which is this one. If I draw that to the left, what has to happen? Toward the horizontal, right? Like this?
Yeah, the red dot thing over there.
Okay, how about to the right? Drum roll. The vertical asymptote's in my way, so I must go up or down.
Up. There's no more x-intercepts.
There's no more x-intercepts. You can't go down. You've got to go up. So look, I know my drawing makes you think go down, because the way I curved it. But when you actually get over here, you're like, oh shit, I can't go through the x-intercept, so I've got to go up.
Why can't you do it?
Because I said so.
Oh,
Because then you would punch through the x-axis, which means you'd create an x-intercept that you don't have. All right, then once you get to a vertical, you have to like jump over and grab another point. So grab this one, that's the next one as I move from left to right. I have to draw to the left, to the right. I will connect dots this way, but to the left, what do I have to do? I have to go down, right? I can't turn back up, so I have to go down. And then here, connect the dots, and then flatten down like this.
So on both ends, you're actually crossing the vertical.
You see, yeah, see, that's why this is a perfect example of why you would never want to draw your horizontal all the way across. Because if you did, and you were trying to draw this piece right here, you might get confused, right? But if it's not there, then you're going to feel free to go over here like this. Yeah, same thing over here, right? You're turning up. Don't worry. This is over here on your left end. Don't worry about it. Yes?
If you have to test a point at each end, where's the third point have to go? Like the test points.
Okay, so look at it this way. You're going to have on your line, I'm going to mark them with X's. These are either going to be X-intercepts or verticals. See, I have a vertical and an X-intercept. Let's just count these as 2 marks, okay? So 2 marks. Then your 3 test points must be on each side and in between.
Okay.
I don't know if that makes sense.
So is there always going to be a vertical and an X-intercept?
You won't always have one. So
What do you do if you don't have one of them?
if you have 2 verticals, you have to pick one between.
Okay.
If you have 2 X-intercepts and no verticals, you pick one between.
Okay, so we have to have it like on each side of the vertical.
Yeah, see, I try and say it in here, but it doesn't work very well when I try and, where is it? Test points should be between X-intercepts and vertical asymptotes. You also need one at each end, so I don't know. Yes, okay, so now we come back to the very beginning, right? And I almost forgot it, the hole, right? So I come back over here, it was at -2. I go up to my function, there's where the hole should be. So I get my eraser out and I put a hole. The hole should not be confused with the solid dot, okay? All of these are solid dots, right? Everywhere where my line is, my curve, those are all solid dots. But right there I have this hole, this missing piece, yes?
So if we tested 4 on there and it came out under the horizontal asymptote, like how do
Okay, that's a great question. So there will be some variations. Let's say you actually did test 4 and it did come out underneath here, which it probably would. Then your graph would just change, it would look like this.
Okay.
But see, remember what we're trying to say is that we can tell where it's above and below the x-axis. We both have that information here. I don't know how high it goes. You don't know how high it goes.
Okay.
All right?
So,
Yes?
so we could draw it either way.
Either way. That's right. Like if I would have picked this test point, it came out positive. If I would have decided to put it here, then my graph would have looked like this. Here, hole, then up. Okay? So there will be some slight variations in our pictures, but they will all have general characteristics that look the same. Yeah. Okay? We good? We good? Now, let's see what we have in terms of practice for this. No, I haven't decided what I'm going to do for the homework yet. How about I send you an email with it? I need to look through the book to make sure. You know what? I'm going to end class early, so I'll be able, early, like 5 minutes early, I'll be able to look through someone's book just to verify the homework is okay, all right, for this section. But we want to talk briefly just about where these rational functions come into play. Has anyone here ever seen the movie Fight Club?
Yes.
Yeah, all the guys. Yes, oh yes, I've seen that movie. But you can, okay. All right, so if you've seen the movie Fight Club, it has this quote. The main character works for an insurance company for cars, like vehicle insurance. And he says in the movie, on a long enough timeline, the survival rate for everything drops to 0. Okay. Time. So what we're saying is that, if you're, let's say, alive at some point in time, we call that time 0, right? Then the probability that you're actually alive 1 year later is going to be different than it was right at this moment in time, right? So maybe the probability that you'll be alive in a year is still pretty good. Might even be better because maybe your health's changed, but the probability that you're alive is going to fluctuate, maybe, right, as time goes on. But on a long enough timeline, this is what he says, on a long enough timeline, the survival rate for everything drops to 0, which means that eventually this trends downward until you get to a point where the timeline still continues. And the question now becomes, does it ever touch the x-axis?
Where you gonna die?
We're talking about probability, though. When you talk about probabilities, you're talking about events that haven't occurred. I'll give you an example. I don't have a coin in my pocket. But if I take a coin right now, and I were to say, all right, here it is, and I flip it, okay? Sorry, misdropped it. Hold on. God damn it. So I flip it, right? Catch it, whatever, do all that stuff. And then I say, what's the probability that it's heads?
50%.
50%? Okay, that's incorrect because the event already took place. So there is no, this is important. Probabilities are about things that have not taken place. So before I flip the coin, I say, I'm going to flip the coin. We're either going to get heads or tails, so it's 50-50 probability, right? Understand the difference? So probability is an event that has not occurred. So when we're talking about this, I'm talking about the probability that I'm going to be alive sometime in the future. I'm not there yet. So I can't make an X-intercept. An X-intercept would be, okay, yes, you're talking about a person that died. But I'm looking back here and I'm saying, here I am right now. What's the probability later that I'm alive? I can't predict exactly when I'm going to die. Yes? Understand the difference? Yeah. So can you ever put this into the x-axis? No, you cannot. This keeps going to 0. Does it ever get there? Never does. Never does. Probability is going to be trending to 0. This is what rational functions are good at modeling, okay? Because that's what we want to do. We want to take real-world situations. We want to model them with mathematical functions. Rational functions are really good at doing this sort of thing. They're not the only types that do it, but they're really good at it. So do y'all like that? Do y'all like the idea of it going to 0? So like, what's the probability that someone lives to be 200? 0?
Well, no. With medical advances,
It's never happened, right?
we don't know what's, they said medical advances.
So you think probability is pretty small? Can you say 0?
Oh, it's got to be greater than 0.
It's got to be greater than 0. What's the probability that someone lives to be 1,000 years old? Very small, but still probable? Still has probability greater than 0?
The stars align.
If they invent new technology to have it to 0.
So that's the key. The key to this horizontal asymptote is a number that's bigger than 0. It might be infinitesimally small, but it's bigger than 0. And that's an important thing to have in mathematics and statistics because you can't say never sometimes.
You ever see Talladega Nights?
It's been a long time.
Which one?
Ricky Bobby?
Well, yeah.
Yeah, I don't even remember one, but he's all like, no one's going to live forever. He's no one is going to live forever, but with my high level of income, and
Oh, yeah. It's like the probability of...
I'll have to go back and I don't know if I've ever seen that one now.
It's funny.
Now I think
It's
about
on
it.
Netflix, if you have it.
So y'all are okay with that. Most of my classes don't like that idea. They're like, well, no one can live to be 1,000 years old. And it's got to be 0. And
Well, there's actually this one thing, it was like...
are we
they
wrapping
kept
up? Can I see the book?
And they said, like, if all this stuff happens, and this, and this, and this, it's possible.
I mean, if you take out
Actually, isn't. I don't know if it's just all that. Yeah, it's just like the no fat. It's like my mom. They said the same amount of calories. What they said, I was watching the show, they said it's not really, she's allergic to it, it's allergic to specific types of food like.
I've got some. I should have done sociology instead? You think I'm not doing this okay? I appreciate the honest opinions.
I didn't say that, but you brought it out, so.
All right, I'll take it. I'll take it. Okay, so I'm going to give you the homework assignment on the board. I'm sorry. You can take a picture of it. Because there's certain problems I need you to avoid right now. This is coming off of page 365. Seven. 9. Those are kind of like baby problems to get you going here. 11. And then these are going to get a little more complicated. Oh no, these are just homework. This is just you should do these. You want to do well in this class, you should do these. 23. 35. Try those. Now those are all graphing rational function problems. So that's quite a bit of work involved there. Next class we will do a little more of this. Just a little bit more, which will take half the class, and then we'll see where we are. Everyone have a good day. Don't forget to recycle these on your way out, please.
No, I need to take a picture of that.